Hey guys, bit of a special video today. So as you can see, I've got all of the parts here that I need to upgrade the current QB in its wonderful form to the newly designed changes essentially that I've all made to the drive pods with the drive pod couplers and various other changes that I've made, as well as I've printed it all in a nice new cool black and white so we can see everything that's going on when it's moving up and down. So by the end of this video, she'll have drive pods for the first time. Both of them will elevate. I think I've got all the parts here that I need. Elevators here and here. Drive pods. Two of these drive pods have been augmented to have the new encoders that I'll talk about in another video. We've got the encoder wheels here for being inserted into the wheels there, and yeah, various other bits and pieces. But what I'm going to do is time lapse this whole thing so that you get to see it being built and then the finished result. See you on the other side. Okay, we made it, but there's a few learnings. First one is that weight is going to be a serious issue on this thing. As much as I'm happy with how much I've reduced the weight so far, it definitely needs to come down. You can see I've shaved edges and corners off a whole bunch of things. Actually, it's really difficult to see now that I've made it all black, so maybe I'll change it all back to a different color. Ultimately, it needs to be black in the middle to shield the light from coming through the skin. But anyway, so there's various components which have got... Let's see if I can get the camera to focus on that. Here we go. It's a bit easier to see there. You've got these edges that I've shaved off to try and create some weight savings and other various bits and pieces. Also, I don't have the encoders installed yet in these front wheels. I've just literally put the motors in, so it looks really cool. It's all definitely coming together as I want it to, and it works. But as you'll see in a second, the servos struggle. Now I've got some ideas and some solutions around that, but let's have a look how she goes. So standing. And you can see there, definitely an issue with servo power. And back to retracting, up to standing. And the brakes all work quite well, so these wheels are in motion. It's a relatively sturdy contraption. I'm not feeling like if it went too fast it would fall over, or if it broke, that it would topple or anything like that. So I'm pretty happy with that. You can definitely feel the resistance on the brakes, so there's no issue with the servos being disengaged and there being absolutely no power going to those servos at the moment for battery saving, which is great. These brakes are definitely doing their job. But where I think the issue lies is in some of this circuitry. So what I've originally put in here, and I'll see if I can find something to point with. There we go. What I originally put in here is this is an Adafruit battery. So a LiPo control circuit essentially does all of the charging and power boosting. So it's got a bit of a boost converter in there as well, up to 5.2 volts, I think it is. This was, a good idea. I didn't really know how much power I was planning to draw. It's got an upper ceiling of around 1 to 1.5 amps, and I'm feeling like, even though I'm not able to measure it properly, I'm feeling like we're drawing closer to 1.8. When all those servos, I've done the math, all those servos look like they draw about 1.8 amps when all operating in tandem and all under strain in their sort of break or stall current. So, I need to accommodate for that. So I think I'm going to have to change this out, put an isolated battery charge circuit, and then straight from the 3.7 LiPo battery, push out to a boost converter to 5 and or 6 volts. So this boost converter down here is fine. This is the 6 volt regulator. I'm sorry, wrong terminology. 6 volt regulator, which is taking the output from the LiPo charge circuit and it's cranking it up to then drive the servo. So all the servos are connected to that directly. But I just don't think it's being delivered enough current straight from this battery control. So if I connect this straight to the battery, it'll be able to draw what it needs to. This is a 2400 milliamp hour battery capable of delivering 2C. So it should be more than enough current, but I don't think this is getting it, and that's definitely going to be an issue. And as the battery gets a little bit, even after 10 minutes of usage, you can see the little flat battery light flick on and flick off on here as all servos operate in conjunction. Now, if you add that into the mix, that we've also got 4 gear motors, which draw somewhere around 450 milliamps each at their stall. So that's another, in isolation, just those motors on their own operating somewhere around 1800 milliamps, 1.8 amps. We've definitely got a power issue, I'm thinking. So I'm going to crank up the battery. I'm going to crank up the LiPo charger and the boost converter and see whether or not we get a better performance. But in the meantime, I'm just really enjoying watching it do all its tricks. So this is it doing a sit. There we go. Plonk. So it's got its front legs out and its back legs down. Back to a standing position here. Yeah, a little bit wonky, but that's just timing, and it's just speed. So I'm hoping that once again, as I get more power, the servos will definitely have a little bit more grunt to do everything all at the same time. What else have I discovered while we're here? Yeah, that's right. So I'm also looking at putting in a dedicated servo control board rather than doing all of this pulse width modulation myself. So here I've got the 2 MOSFETs that control the power to the brake and the elevator servos. So there's 2 servos connected to each one of these MOSFETs, and I can programmatically turn them on or off to save power. And then obviously I've got 1, 2, 3, 4 control cables for the pulse width modulation that goes to each servo to tell them what position to be at. I'm using a hell of a lot of pins at the moment on the microcontroller, so I've got at least 3 more servos to add for the pan and tilt mechanism for the head. Those servos are going to take up more pins. So if I get a dedicated servo control board, then I can simply pump it full of power and send it 2 pins being it's similar to what you see here, these 2 white cables here, which are going to this current monitoring. These 2 white cables here, which are going to this current monitoring circuit, they communicate via I2C. So it's a simple serial interface which can be daisy chained, and they all have unique addresses. So pretty much everything will be controlled via I2C. Simply send a command to those servo control boards and say, hey, this is what position I want it to be at. How that plays with my power on, power off, and braking to conserve power, we're going to have to find out. But I've got one of those in the mail already. Should be here in a couple of days. But that's going to be a big task, so that will be a significant redesign of this whole little, collection of microcontrollers that I've put together for each individual purpose. So once I figure out what direction I want to go there, all of that will be redone. In the meantime, I am going to work on setting up a socket server for the ESP32. I'm really not comfortable with the Blink application and all the data going through the cloud. So just to recap, basically what happens at the moment is I've got a library sitting on the ESP32, which is the brain. On boot up, it will connect to the Blink servers, which are in the cloud. And then whether I'm using the Android app that I've built or that I've connected using their interface, or whether I'm using the API that I've created for my own web application, every message goes up to the cloud and then back down through their live push system back to the onboard library, which is sitting on that chip. It's too slow. And I've got a pretty good grasp of Node and sockets. So I'm going to build a WebSocket server, run it on the ESP32, and then in my Angular app that I'm building at the moment to create the control mechanism, I will connect directly over Wi-Fi to that chip on the local network, hopefully reducing latency to mere milliseconds, 2 or 3 milliseconds, which will give me the opportunity to drive it. At the moment, driving it manually, not that I really want it to drive manually in the end, but driving it manually at the moment is an absolute nightmare. So we'll see how that all goes. But yeah, hopefully you enjoyed that time lapse. You probably also noticed that I printed a few parts in the meantime. A few things broke as I was assembling it. But sit, Bobo, sit. Stand. And retract. There we go. But that's it. All right. Cheers.